Welcome to the deep dive. Today we are really getting into it. Tackling a giant. Albert Einstein. His name basically means genius, right?
It really does. And we've got a huge pile of sources here, looking at his science, his life, his whole worldview.
Yeah, and our mission really is to get past that famous image, the hair, the equation, and understand the core ideas, the struggles, the whole picture.
Absolutely. You hear Einstein, you think EMC2 coloreds.
No.
Instantly. The world's most famous equation, people call it.
It's the headline, for sure. But here's a thing that always gets me, and maybe gets you too. He didn't win the Nobel Prize for Relativity.
Nope, that's a crucial point. The 1921 prize was officially for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect.
Which tells you something, doesn't it, about how radical relativity seemed at the time.
Oh, definitely. The Nobel Committee was playing it a bit safe, you could say. Relativity was just too controversial, too much of a shakeup back then.
But the photoelectric effect, that was quantum stuff, right?
Yeah.
Also revolutionary, but maybe slightly easier to award.
Exactly. It fit sort of into that emerging quantum picture, even though quantum mechanics itself was still pretty contentious. It was a safer bet for them.
Okay, so that's our goal for this deep dive. To really unpack the man who, let's face it, redefined reality. How did these incredible ideas come about? Not just from pure brain power, but, amidst all the chaos, politics, personal life, even isolation later on.
Yeah, it's quite a journey. Let's start at the beginning.
And the beginning is kind of surprising, isn't it? Born 1879, Ulm, German Empire, secular Jewish family. But the key thing, his parents were genuinely worried.
They were, because according to the stories, he was slow to start talking. Really slow.
It's almost hard to believe the guy whose name is synonymous with genius was initially thought to have maybe a learning issue.
It's wild. But then comes this moment, age 5. He's sick in bed. His father gives him a compass.
Just a simple compass.
Yeah, but for young Albert, it was like a revelation. This needle always pointing north. There had to be some invisible force, some hidden order. He talked about it later, saying something deeply hidden had to be behind things.
And that fascination with invisible forces, particularly electromagnetism, it just stuck with him his whole life.
It absolutely did. And that innate curiosity, that drive to understand the hidden stuff, it immediately clashed with the German school system.
Right, the Luitpold Gymnasium. He found it really stifling. All that rote memorization, he called it harmful to creativity. Didn't like the discipline at all.
He was already thinking way beyond the curriculum. He basically taught himself advanced math. By 14, the sources say he'd mastered algebra, calculus.
Euclidean geometry, too. And apparently he even came up with his own proof for the Pythagorean theorem. Just for fun.
Seems like it. He had this incredible confidence even then that the universe could be understood as a kind of elegant mathematical structure. A family tutor apparently said his math genius was just too much to follow.
And he wasn't just doing math. He was reading philosophy. Kant's Critique of Pure Reason at age 13. Seriously.
Yeah, really digging into the big questions early on, thinking about how we know what we know.
Okay, so this independent streak, this dislike for authority, it plays into his next big move, right? Getting out of Germany.
Definitely. He renounced his German citizenship from the Kingdom of Württemberg, technically in 1896. He was only 17.
And the main reason was?
To avoid mandatory military service. He just couldn't stand the militarism, the nationalism.
So he aimed for Switzerland. But didn't he stumble a bit trying to get into the Polytechnic school, the ETH in Zurich?
He did, yeah. He aced the physics and math parts of the entrance exam, but failed the general subjects section. So he had to go finish secondary school first at another Swiss school.
But he got in eventually. And then, crucial step, he got Swiss citizenship in 1901. Kept it his whole life.
That Swiss identity was really important to him. Okay, so he graduates, but finding an academic job, not easy.
Apparently he rubbed some professors the wrong way. Not great at playing the academic game.
Seems that way. He couldn't get a university post for about 2 years. Then finally, through a friend's father, he lands this job. Assistant examiner, level 3.
At the Swiss Patent Office in Bern. From 1902 to 1909. Sounds kind of boring, right? Stamping patents.
You'd think. But this period was absolutely fundamental. He wasn't just rubber stamping. He was analyzing inventions. Things like gravel sorters, electric typewriters.
Okay.
But crucially, lots of devices involving transmitting electrical signals and synchronizing clocks over distances.
Ah, okay. So his day job was basically forcing him to think constantly about time, distance, light speed, synchronization.
Exactly. Practical problems. How do you perfectly synchronize 2 clocks far apart, given that light takes time to travel? These weren't just abstract thoughts. They were tied to the technology he was evaluating every single day. It was the perfect incubator for special relativity.
And he wasn't just thinking alone in the office. There was the Olympia Academy.
Right. This informal discussion group he had with a couple of friends in Bern. They'd read and argue about philosophy, science, thinkers like Hume, Ernst Mach.
Mach was important, right, with his emphasis on observable phenomena, rejecting stuff you couldn't actually measure.
Like the luminiferous ether. Yeah, Mach's skepticism about unobservable theoretical constructs definitely influenced Einstein's thinking. Focus on what you can actually test and measure.
Okay, so all this thinking, the physics, the philosophy, the practical patent work, it all builds up and then just explodes in one year, 1905.
The annus mirabilis, the miracle year. It's just unbelievable. While still working that full-time patent office job, he publishes 4 papers that completely changed physics.
4. In 1 year. Let's break them down, because each one is huge. First,
The photoelectric effect. This is the one that eventually won him the Nobel Prize. The puzzle was about light hitting metal.
right, shining light on metal can knock electrons off. But classical physics couldn't explain why it depended on the light's color frequency, not just its brightness.
Exactly. Classical wave theory said brighter light, more energy should always work. But it didn't. Einstein's solution. Light isn't a continuous wave. It comes in little packets, little bullets of energy. Quanta.
Which we now call photons.
Right. And each photon has an energy based on its frequency. If a single photon doesn't have enough energy to knock an electron out, it doesn't matter how many photons you throw at it. Bang! Light is a particle, at least sometimes. Huge step for quantum theory.
Okay, number 2. Brownian motion.
This one sounds less flashy, maybe, but it was incredibly important. It was about the random jiggling motion of tiny particles like pollen grains suspended in water.
You can see it under a microscope. They just dance around erratically.
Yeah, and Einstein provided the mathematical explanation. He showed this random dance was caused by the constant, invisible impacts of water molecules hitting the pollen grains.
So this was basically the first convincing experimental proof that atoms and molecules were real.
Pretty much, it nailed it. Before this, atoms were still kind of theoretical for some people. This paper made them undeniably real and validated statistical mechanics. Big debate settled.
Okay, number 3. The big one for his popular image, special theory of relativity.
The big one indeed. This tackled a major conflict in physics between Newton's mechanics and Maxwell's equations for electricity and magnetism.
The conflict was about the speed of light, wasn't it? Maxwell's work suggested it was constant, but Newtonian physics implied it should change depending on how fast you're moving.
Precisely. Einstein's radical move was to say, Maxwell is right. The speed of light in a vacuum, C, is always the same for everyone, no matter how they're moving. It's the ultimate speed limit, the one true constant.
But if the speed of light is constant, then something else has to give, right?
Exactly. Space and time themselves have to become relative, flexible. They stretch and shrink depending on your motion relative to what you're observing.
Mind-bending stuff. Okay, and paper number 4.
Mass-energy equivalence. This came directly out of special relativity. It's the equation, 1 2 thalers.
Energy equals mass times the speed of light squared. We all know it, but what does it mean?
It means mass and energy are fundamentally the same thing, just different forms. Mass is a form of energy, a tremendously concentrated form.
And because c, the speed of light, is a huge number, and you square it.
It means a tiny, tiny amount of mass contains an absolutely gigantic amount of locked-up energy. This unlocked the understanding of nuclear power, how stars shine, everything.
4 papers: photoelectric effect, Brownian motion, special relativity, EMC22, all in 1905, from a patent clerk.
It's staggering, just utterly staggering.
Okay, so special relativity lands, and the implications are, well, huge. You said space and time become relative.
Yeah, absolute space and absolute time, the Newtonian bedrock, gone. If I'm watching you fly past me at near light speed, I'll see your clock ticking slower than mine. That's time dilation.
And I'd look shorter in the direction I'm moving. Length contraction.
Exactly. And crucially, because the speed of light is constant for everyone, there's no need for that hypothetical luminiferous ether everyone thought light waves had to travel through.
Oh, right, the invisible jello filling space.
Kinda, yeah. Special relativity just wiped it off the map. If light doesn't need a medium to define its speed, then the concept is just unnecessary baggage, no more universal rest frame.
And then Hermann Minkowski comes along a few years later in 1908 and gives it this geometric twist.
Right, Minkowski showed that special relativity makes more sense if you think of space and time not as separate things, but as interwoven into a single four-dimensional fabric. space-time.
That sounds like a key step towards the next big theory.
It was, because Einstein, even after 1905, wasn't satisfied. Special relativity only worked for smooth, constant motion, what physicists call inertial frames. It didn't include acceleration, and importantly, it didn't include gravity.
So he needed something bigger.
Mm-hmm.
General relativity. Took him another 10 years, right?
Yeah.
Till 1915.
Yeah, it was a long, hard slog, a real intellectual struggle. The big breakthrough idea came earlier, around 1907, with the equivalence principle.
Okay, the equivalence principle, what's the core idea there? In simple terms.
Imagine you're in a sealed elevator, way out in deep space, accelerating upwards. You'd feel a force pinning you to the floor, wouldn't you?
Yeah, feels just like gravity.
Exactly. Now imagine the elevator cable snaps on Earth and you're in free fall. You'd feel weightless, right?
Right. Floating, like being in space.
That's the essence. Locally, you cannot tell the difference between being accelerated upwards and being in a gravitational field. And you can't tell the difference between floating freely in space and freely falling in gravity.
So gravity and acceleration are equivalent. Two sides of the same coin.
Locally, yes. This insight was the key. It let Einstein think about gravity not as a force pulling things through space, like Newton thought,
But as
as a feature of space-time itself. Mass and energy actually warp or curve the geometry of space-time around them. And what we feel as gravity is just us following the curves in that warped space-time.
wow, okay. So planets orbiting the sun aren't being pulled by a force. They're just following the straightest possible path through the curved space-time created by the sun's mass.
You got it. He needed some heavy-duty math to describe this curved geometry, Riemannian geometry, but that was the core concept.
And this new theory, general relativity, it actually explains something Newton's theory couldn't, right? Mercury's orbit.
Yes. Mercury's orbit has this tiny wobble, a precession, that couldn't quite be accounted for by Newtonian gravity. GR predicted the amount of wobble perfectly. That was a huge early success for the theory.
But the real headline grabber, the thing that made him a global celebrity, wasn't Mercury. It was predicting that starlight would bend.
Gravitational lensing, yeah. GR predicted that the sun's immense gravity should actually bend the path of light from distant stars as it passes nearby.
How could you even test that? You can't see stars near the sun normally.
You need a total solar eclipse. When the moon blocks the sun's light, you can briefly see the stars close to its edge. So, in 1919, Sir Arthur Eddington led expeditions to photograph the stars during an eclipse.
Yeah.
And the stars' positions were slightly shifted, exactly as Einstein's theory predicted. The light had bent.
That must have been massive news.
Oh, it was an absolute sensation. Front-page news worldwide. The Times of London had that famous headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." That was it. Einstein became the icon.
Okay, so he's got GR. Now he applies it to the whole universe.
Yeah.
Cosmology.
Right. In 1917, he tries to model the entire cosmos using his equations. But there's a problem. The equations naturally suggested the universe should be dynamic, either expanding or contracting.
But everyone back then kind of assumed the universe was static, eternal, unchanging.
That was the prevailing view, yeah. Seemed more elegant, philosophically perhaps. So Einstein, to make his equations fit that static picture, added an extra term.
The cosmological constant, lambda, like a sort of cosmic anti-gravity.
Pretty much, a constant energy density everywhere in space that would perfectly balance gravity and keep everything stable. The Einstein world model.
And this is what he later called his biggest blunder.
That's the famous story, because just over a decade later, in 1929, Edwin Hubble's observations showed that distant galaxies are moving away from us. The universe is expanding.
Oops.
Yeah. So Einstein ditched the static model, embraced the expanding universe ideas from Friedman and Lemaitre, and reportedly said adding the constant was a big mistake because he'd missed the chance to predict the expansion himself.
But wait, isn't the cosmological constant back in fashion now?
It is. That's the amazing twist. We now think there is something like a cosmological constant, we call it dark energy, that's causing the universe's expansion to accelerate. So his blunder term, introduced for the wrong reason, actually turned out to be incredibly relevant, even prophetic.
That's wild. And there was another twist recently, something about a steady state model.
Yeah, this is fascinating. A manuscript from 1931 turned up, showing that right after accepting Hubble's expansion, Einstein briefly explored a different kind of expanding model.
Not the Big Bang type.
No, a steady state model. The idea here is the universe expands, but its overall density stays the same because new matter is continuously being created out of nothing to fill the gaps.
Wow. like Hoyle and Bondi and Gold proposed much later.
Exactly, years before them. He worked on it, wrote down the equations, showing how new particles of matter must be continually formed to keep the density constant.
Did he stick with it?
No, he seems to have abandoned it pretty quickly, but it just shows his incredible intellectual restlessness. Even when accepting expansion, he was immediately thinking outside the box, exploring alternatives, always questioning.
Okay, so relativity made him famous, dealing with gravity and the large scale. But we can't forget he was also absolutely pivotal in the other great revolution of 20th century physics, quantum mechanics.
Absolutely critical. People sometimes forget this because he became its biggest critic later on. But his early work was foundational, that 1905 paper on the photoelectric effect, giving us the photon. That's pure quantum.
So he established the particle nature of light.
And he was central to developing the idea of wave-particle duality, that things like light and even matter can behave like both waves and particles depending on how you look at them.
And he came up with the idea behind lasers.
Well, the fundamental physical principle, yes. In 1917, he proposed the concept of stimulated emission. It's the process where incoming photons can trigger atoms to release identical photons. That's the mechanism that makes lasers and masers work. Decades before they were built. Pure theory predicting a technology.
Wow. In his work with Bose.
Right. Satyendra Nath Bose sent him a paper in the 1920s. Einstein translated it, recognized its importance, and extended it. This led to Bose-Einstein statistics, a way of describing particles like photons. And it predicted this bizarre state of matter.
The Bose-Einstein condensate.
Exactly, where at super low temperatures, atoms basically lose their individual identities and merge into a single quantum state. It took until 1995 to actually create one in the lab, but the prediction came from their work in the 20s.
Okay, so he helped build quantum theory brick by brick.
Yeah.
But then he turned against it, or at least against the way it developed after 1925.
That's the great irony. As the full theory of quantum mechanics emerged with Heisenberg's uncertainty principle, Schrödinger's wave equation, it became clear that at its heart, it was probabilistic. It dealt in chances, not certainties.
And Einstein hated that randomness.
He profoundly disliked it. He couldn't accept that the universe, at its most fundamental level, operated on chance. This is where we get his famous line, "God does not play dice."
He thought quantum mechanics, even though it worked incredibly well in predicting results, must be incomplete, a stepping stone to something deeper.
Precisely. He believed there had to be an underlying deterministic reality that quantum mechanics was only giving us a fuzzy statistical picture of.
And this led to famous arguments, right? With Niels Bohr.
Oh, the Bohr-Einstein debates are legendary. They went back and forth for decades, mostly through published thought experiments. Einstein would devise clever scenarios trying to show quantum mechanics was inconsistent or incomplete, and Bohr would usually find a way to counter his arguments, defending the standard probabilistic view, the Copenhagen interpretation.
It was like a battle of titans over the very nature of reality.
It really was a fundamental clash of philosophies. Determinism versus probability.
And Einstein's most famous attack on quantum mechanics completeness was the EPR paradox, with Podolsky and Rosen in 1935.
Yes, EPR.
Yeah.
This is maybe his most subtle and consequential critique. It focused on a really weird quantum phenomenon called entanglement.
Entanglement. Okay, what's the basic idea?
Imagine you have two particles, say, created together in a certain way so their properties are linked, like two coins flipped at the same time that are guaranteed to land opposite ways, one heads, one tails. They fly off in opposite directions.
Okay.
Quantum mechanics says until you measure one particle, its state is undetermined. It's maybe 50-50 spin up or spin down. But the moment you measure particle A and find it spin up, you instantly know particle B, no matter how far away it is, must be spin down.
Instantly. Even if it's light years away. That sounds spooky.
Spooky action at a distance was Einstein's term for it. That was exactly his problem. It looked like information. The result of the measurement on A was traveling to B faster than light, violating his own special relativity.
So what was his argument in the EPR paper?
He used this to argue for what they called elements of reality. If you can predict with certainty the state of particle B without disturbing it, just by measuring A, then that state must have been real and predetermined all along.
Meaning there were some hidden variables, some instructions the particles carried with them from the start, dictating the outcome.
Exactly. Hidden variables that quantum mechanics wasn't accounting for. Therefore, he concluded, quantum mechanics must be incomplete. Wasn't telling the whole story. He wanted to restore locality, no faster than light influence, and realism, properties exist before measurement.
It sounds like a powerful argument. Did it work? Did it disprove quantum mechanics?
Well, not in the way he hoped. For decades, it was mainly a philosophical debate. But then, in the 1960s, after Einstein's death, a physicist named John Stuart Bell figured out a way to actually test the core assumption.
Bell's theorem.
Right. Bell showed that if Einstein's idea of local hidden variables was correct, then the correlations between measurements on entangled particles could only be so strong. There was a mathematical limit, Bell's inequality.
But if quantum mechanics, with its spooky entanglement, was correct,
Then the correlations would be stronger than Bell's limit. They would violate the inequality.
and experiments were done.
Yes, starting in the 70s and 80s and getting more precise ever since, and the results are clear. Bell's inequality is violated. Quantum mechanics is right. Nature is non-local, in the way EPR described.
So Einstein's attempt to show QM was incomplete actually led to proving one of its weirdest features is real.
Kind of the ultimate irony, isn't it? As Bell put it, the experiments showed reality works in the way which Einstein would have liked least.
Wow. Okay, so this whole debate and his struggle against quantum randomness, it kind of isolated him from the mainstream later in his career.
It did, especially combined with his other great obsession in his later years, the unified field theory, or UFT.
Right, trying to find one theory to unite everything.
Specifically, trying to unite gravity, general relativity, and electromagnetism into a single, elegant, geometrical framework. He spent the last 2, maybe 3 decades of his life intensely focused on this.
But it never quite worked out.
No. And a big reason was that his approach was purely geometrical. He was largely ignoring the rapid developments in particle physics, the discovery of the strong and weak nuclear forces.
The forces that operate inside the atom.
Exactly. Any true theory of everything would have to include those forces too, but Einstein's UFT attempts just didn't have room for them. So while the rest of physics was exploring the quantum realm and new particles, he was increasingly on his own path, pursuing this unification dream that ultimately didn't pan out.
Before we move to his political life, any other quick mentions of things he worked on? Inventions, experiments.
Well, there's the Einstein refrigerator, co-invented with Leo Szilard, his frequent collaborator. Quite clever, it had no moving parts, just used a heat source. Very reliable.
And they worked on an electromagnetic pump, too.
They did. And one interesting experiment, maybe the only one he personally conceived and carried out, was the Einstein de Haas experiment back in 1915. It demonstrated that magnetism in materials is caused by the angular momentum of electrons, confirming an old idea by Ampere. Showed he could get his hands dirty in the lab too, though theory was clearly his main game.
Einstein wasn't just a scientist locked away, though. His fame gave him this incredible platform, and he really used it, especially when things got dark in Europe.
He absolutely did. 1933 was the turning point. He was actually visiting the U.S. when Hitler came to power, and the Enabling Act essentially cemented Nazi control.
And he saw the writing on the wall immediately.
Instantly. He knew, as a prominent Jew, he couldn't go back to Germany. He publicly denounced the regime and formally renounced his German citizenship while in Belgium.
And the Nazis retaliated quickly.
Oh, yeah. They confiscated his property, his summer home, his sailboat, vilified him in the press. He became stateless again for a while.
But he used his influence to help others escape.
Massively. He became a one-man advocacy group for refugee scientists, especially Jewish ones. He wrote countless letters, lobbied world leaders, Churchill, the Prime Minister of Turkey, others urging them to find positions for scientists fleeing the Nazis.
The sources mentioned his efforts in Turkey saved over 1,000 people.
That's the estimate, yeah. Finding them university posts. It was a major humanitarian effort fueled by his scientific prestige.
And he found his own refuge in the U.S.
Yes, he accepted a position at the newly formed Institute for Advanced Study, IAS, in Princeton, New Jersey, starting in 1933. IAS became a vital hub for many brilliant minds escaping Europe. He stayed there for the rest of his life, becoming a U.S. citizen in 1940.
Now, his relationship with World War II is complicated, especially given his pacifism. The Einstein-Szilard letter.
Right. This is a heavy one. Despite being a committed pacifist his whole life, in 1939, Leo Szilard, the same guy from the fridge, and who first conceived the nuclear chain reaction, convinced Einstein to sign a letter to President Roosevelt.
Why? What was the concern?
Szilard and others were terrified that Nazi Germany was already working on an atomic bomb. The letter warned Roosevelt about this possibility and urged the U.S. to start its own nuclear research program just in case.
And that letter is often credited with kicking off the Manhattan Project.
It was definitely a key factor in getting Roosevelt's attention and mobilizing resources. But this decision weighed heavily on Einstein later.
He regretted it.
Deeply. He later called signing the letter the one great mistake in my life. He said he only did it because of the danger that the Germans would get the bomb first. After the war, seeing the devastation of Hiroshima and Nagasaki, he became an even more fervent advocate for nuclear disarmament and international control.
Signing the Russell-Einstein Manifesto in 1955.
Yes, shortly before his death. A powerful call for scientists and the public to recognize the existential threat posed by nuclear weapons.
His activism wasn't just about war and peace, though. He was very outspoken about civil rights in America.
Very much so. He saw racism in the U.S. firsthand and was appalled by it. He called it America's worst disease. He saw parallels between the treatment of Black Americans and the persecution of Jews in Germany.
He joined the NAACP and supported figures like W.E.B. Du Bois.
Yes, he actively participated. He corresponded with Du Bois, spoke out publicly, and even offered to testify as a character witness when Du Bois was indicted during the McCarthy era.
And there's that lovely story about Marian Anderson, the singer.
It's wonderful. In 1937, Anderson, a world-famous African-American contralto, came to perform in Princeton, but was refused a room at the main hotel because she was Black. Einstein heard about it and immediately invited her to stay at his house.
And she stayed there whenever she visited Princeton afterwards.
She did. It was a simple, direct personal action against segregation, using his status to make a statement.
Politically, beyond pacifism, he had strong views. He identified as a socialist.
Yes, he wrote a famous essay called Why Socialism in 1949. He was critical of capitalism's competitive nature, arguing it fostered selfishness and inequality and crippled individuals. He believed a planned economy focused on social goals was necessary.
And he was a big advocate for world government.
A huge advocate. He saw nationalism and the system of competing nation-states as the root cause of war and conflict. He truly believed that only a supranational authority could ensure lasting peace. It was a consistent theme throughout his later life.
What about his religious views, often described as complex?
So very complex and often misrepresented. He definitely rejected the idea of a personal God, a God who answers prayers, judges people, intervenes in human affairs. He found that concept childish and naive.
So, not religious in the conventional sense.
Not at all. He sometimes called himself an agnostic, sometimes a deeply religious non-believer. His religion was more of a profound awe and wonder at the rational harmony and beauty of the universe, the structure that science could uncover.
Like Spinoza's God, God as nature, as the underlying order.
Exactly. He felt a strong affinity for Spinoza's pantheism, the idea that God isn't separate from the universe, but is the universe's inherent structure and laws. He famously said he believed in Spinoza's God, who reveals himself in the orderly harmony of what exists, not in a God who concerns himself with fates and actions of human beings.
And his relationship with Judaism and Zionism, he was obviously a global Jewish icon.
He was, and he strongly supported Jewish cultural and educational institutions, like helping establish the Hebrew University of Jerusalem. He spoke out fiercely against anti-Semitism, but he was deeply uncomfortable with nationalism, including Jewish nationalism.
So he had reservations about the creation of Israel as a state.
He did. He worried about the potential conflict with the Arab population and favored binational solutions. His support for Zionism was more cultural than political.
Which makes the offer he received in 1952 even more remarkable.
Right. After the first president of Israel, Chaim Weizmann, died, Einstein was formally offered the presidency.
Wow. President Einstein.
Can you imagine? He politely declined. He said he was deeply moved, but felt he lacked the aptitude for dealing with people and official functions, and that his whole life had been focused on objective matters. It wasn't his world.
One last aspect of the man himself, his love for music.
Oh, absolutely essential to understanding him. He was a pretty accomplished amateur violinist. His mother started him on lessons early on.
And he found real joy and maybe inspiration in it.
Definitely. He particularly loved Mozart and Bach. He famously said things like, "I often think in music. I live my daydreams in music." He saw a connection between the harmony and structure in music and the elegance he sought in the laws of physics.
He even had a philosophy about practicing music.
Yeah. Love is a better teacher than a sense of duty, which probably applied to his physics too. Hashtag outro. So Albert Einstein died in April 1955. He was 76. He had a ruptured aortic aneurysm, internal bleeding.
And he refused surgery.
He did. He knew the situation. According to the sources, he said something like, "It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." Just characteristic calm acceptance. He was apparently working on a speech draft almost until the end.
But then there was that really strange incident after his death with his brain.
Yeah, that's bizarre. The pathologist performing the autopsy, Thomas Stoltz Harvey, removed Einstein's brain, supposedly for scientific study, but without getting proper permission from the family first.
And he kept it for decades, sliced it up, sent pieces to researchers.
Pretty much. A weird, controversial footnote. Einstein himself wanted no fuss. His body was cremated and his ashes were scattered secretly, exactly as he wished. No grave, no monument.
But the monument is his legacy, right? Times Person of the Century?
Thanks, Einstein. Unparalleled impact. Eugene Wigner, another brilliant physicist, said while someone like von Neumann might have been faster computationally, Einstein had the truly penetrating and original mind.
And he seemed to have a sense of humor about the whole icon thing.
Yeah.
That story about being mistaken for himself.
Yeah, apparently sometimes when mobbed by people, he'd pretend not to be himself, saying, "Pardon me, sorry, always I'm mistaken for Professor Einstein." A nice way to deflect, maybe.
So when we synthesize it all, this deep dive,
Hmm?
what's the core picture?
It's this incredible arc, isn't it? The young revolutionary who shattered classical physics, redefined space, time, gravity, just brilliant fundamental breakthroughs.
Followed by
The later years, increasingly isolated, battling against the implications of quantum mechanics, a revolution he helped start, and chasing that elusive unified field theory. It's a story of stunning success and, in a way, profound, noble failure at the end.
the ultimate revolutionary who couldn't quite accept the final revolution he'd helped unleash.
That's a good way to put it. He unified gravity and space-time, but couldn't reconcile himself to the dice-throwing god of the quantum world.
Which leaves us, and you, the listener, with a final thought to chew on.
Right. If this man, the very definition of genius, the person who changed our understanding of the universe, spent his last decades convinced that our description of reality quantum mechanics was incomplete, fundamentally lacking something. Well, it makes you wonder, doesn't it? What accepted truths, what scientific models, or even societal norms are we overlooking today? What deeper reality might we be missing just because it seems too weird, too random, too counterintuitive, or maybe just too uncomfortable for us to accept as the whole picture?